Okay, good morning, folks. This is the third week of our EE 353 Power Electronics class, and this is actually the sixth session that we are going to have. Any questions before we start? Okay, so let's take a look at the quiz. We had a quiz last time, so let's take a look at the solution of the quiz. So we had an imaginary component in our system, and we have managed to measure the voltage across this element and also the current that is passing through the element, and the assumption is this is following the passive sign convention. And then part A is asking us about to sketch or plot the instantaneous value of the power, or basically the waveform for that. And if you remember, the instantaneous value of the power is just a multiplication of the instantaneous value of the voltage and the instantaneous value of the current. So all I have to do is just multiply these two signals with each other. If you see from 0 to 3 seconds, my input voltage is at 9 volts. And my input current is actually kind of ramping up. So I'm actually multiplying a constant number with a ramp. So I'm going to just end up having a ramp. And the final value is going to be 9 times 4, which is going to be 36. Okay. Then after 3 seconds, and all the way up to the end of this period, the current is 0. So basically it doesn't matter what the voltage is, the power is going to jump back to 0. So you have a waveform like this with a peak value of 36. Part B, find the average power delivered to this element. So looking at the average power, first of all, you have to identify the period of the signal, which is 10. So we are looking at 1 over 10. Okay. So by definition, this would be our average power. So all you have to do is basically find the area of this triangle and then divide it by 10. And that would give you 5.4 watts. Okay. And part C is asking about the RMS value of the current. So we have this current waveform. We want to find its RMS value. Go back with the original definition of the RMS value of any signal. Like here, we are looking at the current. All right, something like this. So, so if you plug in everything, I'll just copy from one of my notes. My current is 0 beyond 3, so I don't really have to do the integration beyond that. So I'm just doing the from 0 to 3, and you have to find the equation for your current. It's very easy to find, and that would be all right, so basically what I did is I found the description or the equation that governs this line, which would be not necessarily this one. This one is 4 over 3 times time. Okay, so when time is 3, your current is 4. And it starts at 0. So when your current is 0, your time is 0 and the current is 0. So again, if you do the math, you're going to end up having 1.265 amperes. So that would be the RMS value of your current, basically. Any questions? Okay, so it was very straightforward, kind of a, kind of an exercise on getting really good and brushed up on finding the instantaneous value of a signal or the power, or the RMS value of a signal, or finding the average value of a signal. A common mistake would be when it comes to doing this integration, you do a good job, but instead of putting 10 over here, some students put 3. And that's not a good idea, because you're taking the average value of the signal over the span of the period. So please remember here, the number that you should put in there is always your period, not the time interval during which your signal is non-zero. Okay, so No questions? All right, so let's continue. What we did last time was we started chapter 4, and in chapter 4 we are looking at full wave rectifiers. The very first one that we analyzed was a circuit configuration like this, uses 4 diodes, and as it turns out, if you write the equations, your output voltage is equal to the absolute value of the input voltage. So it's always positive, the output voltage, and like here you can see that if this is my input voltage, which is a purely sinusoidal signal, my output signal is like the absolute value of that signal. And we looked at a bunch of other waveforms. For instance, the current that is passing through a particular diode, the voltage that is appearing across a particular diode. This comes in handy when you want to select a diode. And also we looked at the power factor and the average value of the signal and things like that. Then we looked at another rectifier which almost does the same thing but with only 2 diodes, but in addition you also need to have a transformer which as well provides isolation for you guys. So it could be actually a good thing to use this if you have, by complying to some standards, you have to use a transformer anyway, so you can actually use a transformer that is center tapped on the secondary side, so you can use this. Same behavior. Your output voltage waveform is like getting the absolute value of the input voltage signal, assuming that the diodes are ideal. And we, for instance, look at the voltage drop across a diode, and in this particular case, unlike the other one, the peak reverse voltage that appears across the diode is twice the peak value of the output voltage. So this could be considered a disadvantage over here. We can argue that before we had 4 diodes, now we have 2 diodes. The voltage stress on these 2 diodes is twice as much as those previous 4 diode case. One degree of flexibility over here is the term N2 over N1 appears in all our equations. For instance, the absolute value of the output voltage, there is N2 over N1 appearing in that. And this could be good, so that means you have an extra degree of freedom. So for instance, if you want to rectify your input voltage and at the same time boost it up, you can actually use this and achieve that by adjusting the values that you are going to use for N2 and N1. What we are going to analyze today is we are just going to go back to the very original topology that we have, like this guy over here, and then assume that what if our load is not a purely resistive load and there is also some inductance in that load. So we are going to actually come down to basically a diagram like this. So this is what we are going to analyze today. Okay. Which, by the way, it reminds me, before even getting there, I have a table over here which kind of compares a half-wave rectifier versus a bridge rectifier versus a center tap rectifier. So let's just go through this this table. Row number 1 is the number of diodes. So the number of diodes could be an indication of reliability in the system or could be an indication of cost in the system. In the half wave, we only use 1 diode. In the bridge one, we have to use 4 diodes. In the center tap, we only use 2 diodes. So you can actually compare them. Then second row is isolation. Okay? So isolation, sometimes there is a standard that we have to comply with. For instance, you're trying to, I don't know, build a power supply for laptops and it has to comply with some European standard, and in there you need to have isolation. So we are going to see which one of these topologies provide isolation for us. The only one is the one that uses a transformer, which is the third one. So the first 2 don't have isolation. The third row is the average value of the output voltage. All right, the average value of the output voltage. The first topology was only Vm over pi. Vm is the peak value of the input voltage. The second one was twice as much, 2Vm over pi. And the third one is N2 over N1 times Vm over pi. And again, please remember, I discussed this last time, how N2 is defined. Is it the total number of turns on the secondary side or half of the total number of turns on the secondary side? Over here, the assumption is it is the total number of turns on the secondary side. The fourth row is looking at the RMS value of the output voltage. So V out RMS. In the first topology is Vm over 2. In the second topology is actually this signal divided by, multiplied by a square root of 2 basically. So it's Vm over the square root of 2, which is the same as the RMS value of the input voltage. And on the last topology is almost the same. There's only a turns ratio involved. The next row is looking or comparing at the power factor on the input side. If you look at the power factor, again to comply with some standards, the half-wave rectifier, the power factor is about 70% or a square root of 2 over 2. And in the other two ones, it is actually perfect. It's like a 100% power factor, or 1. Then the following row looks at the voltage stress. Voltage stress on the diodes. Okay? So voltage stress on the diodes is important because when we want to select a diode, we have to know how much voltage it should be able to tolerate when it is off. In the first topology, the maximum voltage that appears on the output voltage is the maximum reverse voltage that appears across the diode. In the second topology, same. In the last topology is actually twice as much. So that could be considered a disadvantage for the center tap topology. Then let's look at the current stress on the diodes. So current stress of the diodes is assumed to be the peak value of basically diode, not the RMS value of the diode current. So this is I diode peak. Okay. First topology is Vm over R, assuming that all of these converters are providing power to a resistive load. Second topology the same, and third topology is just an N2 over 2 and 1 involved. And the final row is the fundamental frequency of the output voltage. Okay, fundamental frequency of the output voltage. Okay. So this comes in handy when you're trying to use a filter to filter out a bunch of harmonics in your signal. In the first topology, it's omega. Omega being the angular frequency of the input voltage. The same frequency appears there. In the other two, it's actually 2 omega, meaning that our output voltage is repeating itself twice in one period of the input voltage. Now, this actually could be a good feature, having in a bridge rectifier or in a center tap rectifier, this factor of 2 appearing is a good thing. Now, why is that? Because if you are trying to design, on the output side, if you are trying to design a low-pass filter to eliminate the harmonics of the line frequency, like 60 hertz or whatever it is, 2 omega is larger than omega, so your low-pass filter is going to be smaller. Or if you use the very same low-pass filter, then your attenuation at 2 omega is going to be larger than your attenuation at omega. So basically what I'm saying is, if you look at the Bode plot of a basically, or the transfer function, or the magnitude of the transfer function of your low-pass filter, let's say it has something like this. So on this axis we have frequency, and on this axis we have magnitude of the harmonics. Or this particular is actually the magnitude of your gain. So you can see a low-pass filter, if you are not familiar with it, basically allows low frequencies to pass. For instance, a DC frequency or a zero frequency is what we desire in a rectifier, and kind of attenuates higher order frequencies. So if you design a filter like this, and you're using a half-wave rectifier and omega appears over here, you can see you have a little bit of an attenuation at that particular frequency. But if you use the very same filter and hook it up as the following stage of a full-wave rectifier, you are going to see that you have a larger, basically, attenuation. And that's good. That means there's going to be less ripple in your output voltage. So this could be a good thing in a full wave rectifier. All right, so this table was kind of summarizing the differences between these basic three topologies that we have analyzed so far. All right, any questions? Okay, so let's move on to the next topology. And before even doing that, I have a little bit of a justification why we are actually doing so. So technically what we have done so far is we have become familiar with this H-bridge of diodes, and we know that we have some sort of a load, which is in most cases could be a resistive load. And then the question is, if we are not happy with the waveforms that we are getting on the output side, how can we filter this thing basically? So one approach could be putting an inductor over here as your low-pass filter. Or sometimes your load already has some inductance and you don't really have to add anything extra, or maybe add a little bit extra. And this is actually shown over here. This is the first one that we are going to analyze. Then you may say, oh, inductors are relatively large, they are bulky, they are heavy. I'm looking at the portable applications and I don't really want to use an inductor. Then I may say, okay, use a capacitor in parallel with your load. Okay? And we have already analyzed this in a half-wave rectifier, but we are going to reanalyze it again for a full-wave one. And this is basically demonstrated over here. Or you may argue that I really want to have a very purely DC output voltage. I don't care about the weight and volume of my signal, of my basically converter or rectifier. So I'm going to use a second-order filter, which is comprised of one inductor and then one capacitor. So that's another option that you have. So it's just a matter of how complex do you want your circuit to get, how much money do you want to spend, and in terms of weight and volume, if you have any limitations or not. Now, we are not going to analyze this, but as it turns out, analyzing this is actually going to be quite simple. You can actually run some simulations and get information about it. All right. So let's just start with the first one. The case that either we have intentionally added some inductance in series with our load to filter some harmonics out, or the load by nature has some inductance in itself. So we are looking at basically a full bridge rectifier with an RL load. Okay. Here we are assuming that L is part of our load, but you can say that no, it's not part of the load, it's actually part of our filter. It doesn't really matter. All right. So we have a topology like this. So we have 4 diodes. We have to figure out which one is on, which one is off, things like that. I'm going to make an assumption. The assumption is I'm assuming that this current is continuous and always positive. It never gets negative and it never gets 0. So it's always it's like if you want to plot it, it could be, for instance, if this is your 0 level, it's like hovering around something like this, like between 2 amps and 3 amps. So it's always positive. It does not even touch the 0 level. All right. Now later, when I'm done with the analysis, you have to come back and make sure this assumption was a true and valid assumption. Now, if you make such an assumption, what you're going to realize is, if I have a continuous current over here, that's a mandate for D1 and D4, so that we need to have at least one of them to be conducting at any given time. They cannot be off. Both of them cannot be off at the same time. Because if this one is off, like an open circuit, and this one is off, like an open circuit, then the question is, where is this current going to flow through? So that's not going to happen. You can make the same argument for D3 and D2, that there is not a possibility. It's not possible for both of these diodes to be off at the same time, because that kind of violates the fact that the assumption that I just made, that the current is a continuous current, because then this current is continuous. Then if this is open and this is open, then where is this going to flow through? Okay. So far it kind of narrows down our possibility of basically modes. So basically we have 4 diodes 2 to the power of 4. We have 16 modes of 16 possibilities for D1 through D4 to conduct or being off. So far, we can actually rule out some of them. The other argument that I'm going to make is you can actually the final argument is basically if my input voltage is positive, so let me just assume that my input voltage is positive. So I'm just going to replace it with some positive voltage. Let's say it's 10 volts or whatever. And let me plot all of these diodes, draw all of these diodes over here. And I just assume that my output current is continuous, so I can actually replace it with some sort of a current source. All right? So when Vn is positive, the argument that I'm making is there's only the only possibility is for D1 and D2 to conduct. And there's no other possibilities. For instance, if you assume that D4 is conducting, that is not going to make sense. Okay, so let's look. First of all, between D1 and D4, we know that they cannot both be off, because then that violates the output continuity of the output current. And I can make an argument that in this case, if you look at this loop, let me use a different color. Okay, if you look at this loop, if you redraw this, you basically have a system like this. I'm just redrawing this loop again. And on the top one is D1, the bottom one is D4. So first of all, I know they both cannot be on. I know that they both cannot be off. Now let's assume, what if D1 is off and D4 is on? Does that make sense or not? I'm trying to basically find out what happens to the diode. So if D1 is off and D4 is on, basically the voltage drop that you have from anode to cathode of D1 will be positive. So I just assume that I have a diode that is off, but at the same time it is blocking some positive voltage. That doesn't make sense, so this is not a good assumption. All right, so this doesn't happen. So the other assumption that I can make is, what if D1 is on and D4 is off? Okay, so now if I look at VD4, which is this voltage, actually, as it turns out, VD4 is the opposite of the input voltage, so it's negative Vn. Okay, let me write it here. Okay, so VD4 is negative because the input voltage is positive, and that makes sense. I'm assuming that I have a diode that is off, which is D4, and it is blocking some negative voltage. That makes sense. So when the diode is off, it is capable of blocking negative voltages. So as it turns out, this is our viable mode. Okay. Then you can argue that what if they are both on? And that doesn't make sense, because if you have both of them on, you're basically shorting your input voltage. You're kind of violating KVL. Okay, so you have basically a short circuit here. And because these are diodes, the input voltage source is not going to allow this to happen. So basically, we ruled out both diodes being off, both diodes being on, D1 off, D4 on. So the only viable possibility would be D1 is on and D4 is off when the input voltage is positive. Okay. So we know that this is the one that is conducting, and this one is not conducting. Okay. You can make the same analysis for D2 and D3, and you end up having basically D2 is also on, and then D3 is off. Okay. So when the input voltage is positive, you conclude that D1 and D2 are on, and D3 and D4 are off. And then you can make the same analogy for the case that the input voltage is negative. Let me see if I have to erase a bunch of stuff here. Let me just erase them. All right. So now let's look at the case that the input voltage is negative. So I'm just going to draw it like a negative, like a battery kind of a thing. So here Vn is negative, the second half of the cycle. And my output current is still continuous in this direction. Okay? So if you follow through the analysis that I just made, what happens to D1, what happens to D2, as it turns out, when the input voltage is negative, technically, I have D1 off, D4 on, and D3 on, and D2 off. Okay? So this is how it's going to be. So technically, if you want to follow the path of the current, or how is the output current flowing, basically, the output current is coming from the source, going through D1, going through the load, going through D2, and coming back. In this case, the current is going to flow through, let me start it from here. Flow through D4, goes through the load, comes down to D3, and then goes up here and comes back. All right? So a situation like this. So it's like an 8 kind of a twisted 8 kind of a thing. All right, that's it. So any questions? So if you are trying to monitor, and I'm going to tell you why. If you're trying to monitor this voltage waveform from here to here, in this particular schematic, it is actually identified as the output voltage. As it turns out, if you're plotting this voltage, it is going to be the absolute value of the input voltage. So we have that rectification action going on. What we have to find out is the waveform for the output current. So we kind of know what kind of voltage is going to appear across our load. Basically, this voltage is the same as the input voltage when the input voltage is positive. And in this case, you can see that this voltage is the opposite of the input voltage when the input voltage is negative. So this argument of the output voltage is the absolute value of the input voltage is actually true. All right, so we kind of know what kind of voltage is going to appear on our output side. Then the next question is, okay, what does this current look like? And remember, we also in the end have to make sure that the original assumption that I made is true, and that was the output current should be positive. All right. In order to find this, you kind of have to solve this basically differential equation. You are saying that I'm applying the absolute value of my input voltage, which I just wrote down here, which is equal to my output voltage, which is equal to the voltage drop across the inductor, which is L di over dt, plus the voltage drop across the resistor, which is R times I. And I is basically identifying the output current. So I'm just going to write I O or I out or something like that. Okay. So you kind of have to solve this differential equation to find the output current. Okay. Now there are many ways of doing so. And by the way, you only care about the steady state response of the system, not the transient. There are many ways of doing so. One way that the book has actually done, and it's actually quite an interesting approach, and we are going to do it right now, is basically breaking down our input voltage. I'm sorry, not the input voltage. This is actually our output voltage. Breaking down our output voltage to its harmonics. And basically, this is a periodic waveform. So we just argue that this V out looks like this. All right. If V out was like a purely sinusoidal signal, that would have been very easy, finding the steady state of a system, a linear system. The system only has an R and an L, so it's a linear system, and they are both linear components. It would be like the steady state response from the Laplace transform that you have seen in circuits 1 or circuits 2. In this case, our input voltage, or I'm sorry, our output voltage is not purely sinusoidal. However, it's the periodic signal. So what you can do is you can break down this signal using the Fourier basically series to its harmonics. So I can say this signal is the equivalent of a DC value or harmonic at zero frequency plus V2 cosine of 2 omega t, or maybe sine of omega. Okay, it's a cosine. Let me see if I have sine or cosine. Yeah, my notes are based on cosine, but it would be easier to write them based on sine. But anyways, cosine of 2 omega t plus pi. And then plus V4 cosine of 4 omega t plus pi. And you just keep breaking down into its harmonics. And then for each component that appears in my output voltage, I solve this equation. So if I'm, for instance, considering 10 harmonics, I can actually break down my input voltage to the first 10 harmonics that it includes, and then solve the equation. And then find the current. So once I will assume that my output voltage is just a DC term, then see how much DC term this DC voltage is going to create, how much current it is going to create. Then I'm going to assume it's a cosine of 2 omega t kind of a term. Then see how much current this guy is going to generate. And then again, I'm going to assume that V out is this term. Then look at the current response that I get. And in the end, because this is a linear system, superposition holds. So I can see I can say that my entire output current is the sum of all of these responses that you are going to get. So let me just make this a little bit clear down here. Okay, so I'm saying that this is the equation that we are trying to solve. V out is all right, very simple. And V out turns out to be the absolute value of the input voltage So we are trying to solve this. What I'm suggesting is break this down into its components, like the DC component, and then the component that appears on the second harmonic, and then the component that happens at the fourth harmonic, and just keep doing that. And solve the equation for VDC and see how much current you're going to get. And then solve the equation one more time for the second harmonic and see how much current you're going to get in there. And then the fourth harmonic. And just keep doing that. Then if V out is the sum of all of these, then I out will be the sum of all of these. Something like this. All right? Very simple. So you're using superposition. So let's get to the details of this. As it turns out, because of the even symmetry that my output voltage does have, if I break it down, I'm going to actually have a DC term. We have actually already seen this DC term of 2 Vm over pi. Vm is the peak value of the input voltage. And then a bunch of higher order harmonics, which are actually expressed using this equation. N is the number of harmonic that we are looking at. And as it turns out, because of the symmetry, n is only an even number. So for instance, we don't have a harmonic at n equals to 1 or 3 or 5. We only have non-zero harmonics at n equals to 2, 4, 6, and 8, and so forth and so forth. Okay? So once I solve this equation with a VDC, and the steady state response would be, so technically let me draw it over here. So that means for this part, what I'm doing is I'm assuming that I have a DC signal here. And I'm looking at the steady state value of the output current. Under steady state conditions, the inductor behaves like a short circuit. So the DC component in the output current will be VDC over R. So this is basically this guy over here. All right. Then the second time, for instance, for this guy, I'm assuming that I'm exciting the system with some, I don't know, V2 cosine of 2 omega t plus some phase angle. And then I have to find this current of I2, which will be, looking at the steady state response, will be V2 over the magnitude of the impedance, and then cosine of 2 omega t plus phi minus some sort of an angle, theta 2. And that theta 2 is the inverse tangent of L omega over R. All right? Okay, so this whole thing is your I2. Then repeat that for n equals to 4, that's going to be your I4. Then repeat that for n equals to 6, this is going to be I6. Then add them up all with each other. So the note that I have up here is actually doing that. All right, so for instance, I'm exciting the system with V2 times cosine of 2 omega t plus pi, and then find the corresponding current response. And then another time I am exciting the system with V4 times cosine of 4 omega t plus pi. Then I'm getting this response over here. And you just keep doing that. And if you add them up with each other, this is the response that you are going to receive for your output current. So it has a DC term plus a bunch of harmonics, and each harmonic has an amplitude of I sub n, which is determined here based on the amplitude of the output voltage at that particular harmonic, which is actually calculated here, divided by the magnitude of your impedance evaluated at that harmonic, which is R squared plus NL omega squared. And there is also a phase angle involved, which is the inverse tangent of NL omega over R. Okay? So this is kind of, I don't think you have seen this before. This is kind of a new way of, analyzing things, especially in power electronics. A lot of our signals are periodic, so we can break them down to their Fourier harmonics and then solve it for each particular harmonic. Then in the end, add them up all with each other. So if you do so, and actually I have a file which is actually doing that, the output current is going to look like, if I plot basically this current over here, this current over here, it is going to look like something like this. All right. First of all, it is continuous and it's always positive. So that original assumption that I made, that my current should be positive and continuous, it is true. And that's it. This is how your output current is going to look like. And depending on how much R you have and how much power you're delivering to the system, obviously this is going to go up and down. If R changes, for instance, this would be R increasing. All right. If you are curious about the current of D1 and D2, for instance, first of all, D1 and D2, let me make sure I'm using the same label that the book is using. Yeah. D1 and D2 conduct together, and that is when the input voltage is positive. So when the input voltage is positive, the current of D1 is the same as the output current. Okay, so if I'm trying to plot this in the first mode, during which the input voltage is positive, all I have to do is just follow the trend of the input current, of the output current. So whatever I have here, I'm just going to plot it here. All right, so that's during the first mode, and that is when your input voltage is positive. In the second mode, the input voltage is negative, and as we just discussed, D1 and D2 are basically off. This is off over here, this is D1, and this is D2. They are both off. They are not conducting any current. So basically the current is 0. Okay? And then the next cycle starts, and same thing, and then 0. All right? You can actually plot a similar waveform for D3 and D4, and that's actually the same waveform, only shifted by 180 degrees. And ultimately, the input current, if you are curious about the basically waveform of the input current, IN as input, or as the book is labeling it, IS as in source. This current, if you apply KVL here, is the current of D1 minus the current of D3. So IN is ID1 minus ID3. Please remember, when it comes to labeling the current of a diode, I'm always assuming the diode current is flowing from anode to cathode. All right? So all I have to do is just, I already found ID1, I already argued that ID3 looks like it, only 180 degrees phase shifted. I just have to subtract them from each other. And if you do so, you're going to end up with a waveform like this. All right, so this is going to be your input current. This portion is basically ID1, because ID3, was it ID3 or ID4? Because ID3 was 0. And this portion is negative ID3. Remember, the current of a diode is always positive, so this is appearing negative, so that means it's a negative of ID3. And the sequence continues. So you can argue that you would expect to see a relatively good power factor, because as you see, if I just over plot my input voltage waveform, at least they are in phase with each other. The input voltage and the current of the source are in phase with each other. But I mean, the current that we are drawing is not purely sinusoidal, but I'm assuming that it has a very large AC component at the fundamental harmonic. So you can see that you are expecting to see a very good, relatively good power factor. And we have a numerical example to verify that. One other thing that you can argue is, okay, so if you compare the input current waveform and the output current waveform, which is basically this guy over here, this was I out, you can see that the output current waveform is like the absolute value of the input current waveform. And the same equation held for the output voltage. All right, so please remember these two equations. And remember, whenever we are taking the absolute value of a signal, its RMS value doesn't change. So basically you already saw this in the rectifiers that we were working on last time. All right, we have already seen this, but also here for the current it holds. So I out RMS is the same as I in RMS. So if you have the RMS value of one of these guys, you don't have to calculate the other one. You can just say they are basically the same. All right. Any questions so far? So this might be something new, but it's quite simple. We just break down our output voltage into a bunch of harmonics, then apply each individual harmonic and see what kind of response we get. Then in the end, we use superposition and add up all of the responses to each other to form our entire output current waveform. So the important equations are basically, if I have a harmonic at 2 times omega t, what is the amplitude of this harmonic? So this equation over here is giving that to me. And the current is easy. You just have to divide this by the magnitude of your impedance at that particular frequency with a little bit of a phase lag, and the phase lag is basically, in general, is the inverse tangent of n, the number of harmonics, times L, the value of the inductor, times omega, your frequency, over R. Now, I have a Mathcad file. It's already on Blackboard. I was trying to download it from Blackboard, but I was not successful. Please let me know if you have difficulties downloading it. But anyway, under content, here it is, Mathcad full bridge rectifier with RL load. Okay, this is the file I'm talking about. It's a Mathcad file. And okay, here it is. So I'm making a bunch of assumptions. For instance, I'm trying to basically verify what I just did, add up all of these harmonics and see what they look like. My input voltage is having a peak value of 110 volts RMS times the square root of 2. The value of the inductor that has been used is 20 millihenries. Load resistance is 4 ohms. The frequency is at 60 hertz or 2 pi f radians per second. And obviously period is 1 over f. And here I have actually a counter for my harmonics. I already mentioned that I have harmonics at 0 frequency, which is DC, then twice the line frequency, which is 120 hertz, and 240 hertz, and things like that. So I'm actually using 2K as the N, which was counting our harmonics. So basically this 2K that appears over here is the N that I had in this equation over here. So I have 2Vm over pi, 1 over n minus 1, minus 1 over n plus 1. And if you replace n with 2K, you're going to basically end up with this equation. Now, if you haven't used Mathcad before, I would encourage you to start using it. It's a very useful tool. You can visually see, I mean, you can use MATLAB as well, but I mean, this is a little bit friendlier. I would say not at the beginning, but as you get the hang of it, it's going to be very friendly. And so first thing that I'm going to do is I'm actually plotting these components, basically, these amplitude of the signal. So as you can see, I have a very large DC component. Then at twice the line frequency, which is 120 hertz, I have another component. Then at 4 times the line frequency, I have a smaller component. And as the order of harmonics goes high, the magnitude of these harmonics are getting smaller and smaller because I have division over n or 2k in both of these expressions. All right. First thing that I'm going to do is I'm going to basically verify this equation that was provided to me from the book, basically. So I'm trying to verify, is this equation correct or not? So if this is suggesting that I can break down my rectified voltage waveform into these harmonics. If I add them up all together, I should basically get my original rectified signal. So this is what I'm doing. I'm actually looking at k, or the number of harmonic from 1 to 20, and kind of adding these signals with each other. And as you can see, if I add them up, you are going to end up having a rectified output voltage which we originally had. And obviously, depending on how far you go, let me see, for instance. So if you only add the very first few harmonics, it's close to what we want, but it doesn't really touch 0. Then as you increase the order of harmonics that you are considering, then it gets better. And if you go all the way to 20, it's almost, you can't really identify this signal versus an absolute value of a sine signal. So that equation that was provided to me from the textbook is a valid equation. Now, I have to find the harmonics in my current. So my current has a DC component, which was the DC component of the voltage over R, and then some AC harmonics. And this is the magnitude of those harmonics. And you can see if you look at the frequency spectrum of your output current, you have a relatively large DC component, which is like between 22.5 to 30. And then at twice the line frequency, you have about 5 amps. And then at higher order harmonics, it rapidly basically damps to 0, even better than even faster than the voltage. Why? Because my signal is passing through a low-pass filter. And I'm looking at theta, which was the inverse tangent of n times L omega over R. And in the end, I'm actually adding all of these responses with each other to be able to construct the waveform of the output current. And this is actually your output current. And this basic current is what I drew over here as my output current. All right. Now that we have this, we can actually play around and say, for instance, what if our L is very large? What if our L is very small? Let's actually do that. So just have this waveform in mind. We have a relatively large DC component in that, which I guess is 25, and then a little bit of a ripple on that. And by the way, you can actually decide how many harmonics you want to consider. For instance, let's say if I only consider the DC term, which is I0 over here, and the first harmonic, this is going to be my output current, pretty much close to what I already had. And if I consider the first and second harmonics, it gets closer to a real case. So you can see that I don't really have to go all the way to 20, maybe 4 would be enough. It's close to what I expect. But hey, you know, it's a computer, it doesn't matter, so I just put 20. And you can see it didn't really change much. The reason is the order of harmonics, when k gets larger than 4, is almost 0, so it really doesn't matter if I include them or not, basically. All right. So have this waveform in mind, and let's say, what if our L is a very large error? So instead of 20 millihenry, let's say we wanted to use 200 millihenries. And let's look at the output current. I suspect that the output current is going to get closer and closer to a DC case. So just upgrade it, and I just update it, and it actually does. Now, why is that? Because there is a division by L appearing here in the magnitude of the harmonic of the current. So if L is very large, basically it does a good job in terms of filtering. So when it comes to a steady state, I can actually look at this frequency spectrum and see I only have a very large DC component, and the rest are almost 0. And by the way, the DC component did not change. We are still at 25 amperes of DC current on the output side. So this gives you basically a trade-off on how well you want your output current to be close to a DC current. Okay, like in this case, you can see it's very close to a DC current. Therefore, the voltage drop across the resistor is also very DC if that's your purely resistive load. But the compromise here is you're using a very large inductor, and that means your system is going to be very bulky. It's like 200 millihenry inductor is very large, actually. And on the other side, if I make my inductor very small and kind of eliminate it, I will go back to the original case of having a full bridge rectifier with a purely resistive load. So I'm not going to put it 0 over here, because if I put it 0, the software is going to be unhappy because I have a division by L somewhere. I just make it very, very small. So instead of 20 millihenries, let's say 20 microhenries, okay? And see what happens. All right, so I switch back to the original purely resistive load, a rectifier with a purely resistive load, as if the L does not even exist at all. And if you look at the frequency spectrum of your current, you still have that 25 amp of DC current, but you can see the harmonics are relatively basically large. And what if your power level changes? That means R is changing from 4 ohms to 5 ohms or 40 ohms and things like that. You can play around and actually figure out what's going on. The other thing that I have done over here is I'm looking at the RMS value of the output current. Remember, we have all of the harmonics in the output current. The first session that we had, we looked at the RMS value of the output current, which is the square value of the, each one of these harmonics in RMS terms squared. So that's actually what I'm doing over here. The RMS value of the output current in this case is very close to the DC value, which is 25. Trying to find the output current in this case is about 2.4 kilowatts. And I'm trying to plot the input current, which is this red curve over here, which we already did on one note. And power factor, which is the average value of the power over the apparent power, which is the RMS value of the input voltage times the RMS value of the input current. The RMS value of the input current voltage is very easy to find. It's just Vm over the square root of 2. The RMS value of the input current is the same as the RMS value of the output current. I'm actually referring to this equation over here. All right. So your power factor is 0.9. So you can actually make decisions. If I eliminate the inductor, okay, which we just did, and basically switch back to a purely resistive load or a full bridge rectifier, you can see your power factor will be almost 1. Okay, ideally 1. So from one perspective, from the grid side, I'm making the grid people happy. The power that we are drawing is almost, the power factor is basically ideal. But if you look at the output current, it's not really DC. On the other side, if I make my inductor very large, okay, like 200 milli, to get a relatively DC output current, oops, I haven't updated it. To get a relatively DC output current like here, you can see that your power factor is going to get lower than 1, deteriorate. It's only 0.9. So there is basically a little bit of a compromise here. You can actually decide where exactly you want to stand. So I leave these guys to you. Can down if you have problems downloading. I just had a problem. I don't know if this is this computer or in general. If you cannot download this file, let me know and I can email it to you. Hopefully you will not have any problems. Play around with it, just change the parameters and basically see how everything changes. Now in addition to this, we also have a numerical example to further clarify this thing. Going back to the notes. So here I have an extreme case of L being very, very large, or in other words, L omega is very, very much larger than R. We just saw that in my Mathcad file. The output current tends to become almost DC, and our current waveforms, like the diode current waveforms, they lose their ripple, so they become kind of a square wave, kind of a waveform, and also your input current will be your kind of a square wave. So this is actually your input current. All right? Okay. So let's look at this example. So you can verify this example by this Mathcad file that I've already uploaded on Blackboard. So we have a full wave rectifier with an RL load, and the parameters are given here. Like my input voltage is 110 volts RMS, so peak is 110 times the square root of 2, and the frequency is at 60 hertz. Load is 4 ohms, and the inductor is 20. Actually, it turns out the same numbers appear in the Mathcad file. Maybe I've got them from here. The average load current we want to find, we just found that we're very close to 24 volt, 25 amps. Part B, power absorbed by the resistor, and we have been asked to only consider the DC term and the first 2 AC harmonics in the output current. Part C is asking about the power factor. So So the DC or the average load current would be as if you're exciting the system with the DC component of the output voltage, and just divide that by R, because under DC terms, inductors are like short circuit. So this would be about 24.76, and we see almost same behavior here. If you actually measure this blue dotted line, which is the DC component, actually I can just get the value out. I 0, 24.79 or 6 actually. And the other harmonics are, for instance, I'm considering the second harmonic, and we have been asked to consider the fourth harmonic. So for the second harmonic, I have to consider R squared plus 2 L omega squared. And for the fourth harmonic, this is the square root of 2 for L omega. So pretty much everything is there. The reason that the square root of 2 appears is because I'm trying to get the RMS value. Please remember, this expression over here gives you the peak or amplitude. The amplitude of the harmonic at a particular frequency. If you are interested in finding the RMS value of the particular harmonic, you just have to divide that by the square root of 2. So that's what I'm doing over here. If I'm trying to find V2 that I need in this equation, based on that expression, V2 is basically the amplitude of the second harmonic in the output voltage. So I just have to replace n with 2. So that's 2 Vm over pi, 1 over n minus 1. In this case, n is 2 minus 1 over n plus 1. So this turns out to be 66 volts. And if you calculate this expression, it turns out to be 8.9 amps. This is actually a squared, ampere squared. Then the amplitude of the fourth harmonic in the output voltage is 2 Vm over pi, 1 over n minus 1, n is 4, minus 1 over n plus 1, again n is 4. So this is actually in general an n. Okay? So this amplitude turns out to be 13 volts, and if you calculate this expression, it turns out to be very, very small. So this is kind of a hint for you guys. You don't really have to keep doing this because already your harmonics are getting really, really small. You can see that the second harmonic squared is almost 9, and the fourth harmonic is almost 0.1. Okay? So this expression over here is very important. Let me just rewrite it over here. It's a little bit messy. Remember, if you have, let me show you my notes where this equation is coming from. I don't know if I had it here. No, I didn't have it. Maybe here. Let me just show you the notes. Well, okay. If you go back to the discussions that we had the first week of class, so like here, if I have a signal and this signal has been broken down to its Fourier series or harmonics like this, then the RMS value of this signal is the DC value squared plus the sum of all of the RMS values squared for each particular harmonic. So this is the equation that I'm using over here. In this case, I'm only looking at, so basically I'm looking at IRMS is the square root of IDC squared plus I2, as long as it's an RMS value squared, plus I4, plus, in case you want to consider other harmonics, which we are not. And this equation is basically the same as what I have here. And IRMS turns out to be 24.9 amps, which is very close to our DC component. The output current, we have been asked to find, I guess part B is asking about the power absorbed by the resistor considering the DC component and all of these second and fourth harmonics. So please remember, when it comes to power absorbed by a resistor, okay, first of all, let me go back. if I consider this thing to be my load, the power that is absorbed by the load, means the resistor and the inductor together, is the same as the power absorbed by the resistor. Why? Because the current waveform of this inductor is a periodic waveform. So basically, this inductor is not really consuming any power on average. So any power that we are getting absorbed by the load is actually the resistor is doing that. The inductor is not really doing anything as long as it's an ideal resistor. As long as the inductor is an ideal inductor. So technically, when it comes to calculating the output power, you just have to focus on the resistor. You don't really have to worry about the inductor because the current waveform is a periodic waveform. So that's why when it comes to P out, all I am doing is actually trying to find PR, power loss in the resistor. And any given resistor, if you're trying to find that, it would be IR, okay, times R. So the value of the resistor times the square value of its RMS current. And we already have the RMS value of the current from here. So that's why we were actually finding it. Actually, I even have 622, which is the square value of the RMS current. Just have to multiply this by R, which was 4. So your power turns out to be 2.488 kilowatts. And power factor, average value of the power, which is this guy, over the apparent power, which is V in RMS times I in RMS. V in RMS is 110. I in RMS is the same as I out RMS. So it's the square root of, basically this guy over here, 24.94. And this gives you a power factor of 0.9, which we had it in the Mathcad file as well. So we can actually double check this solution versus the Mathcad file that we have. All right, any questions? So we just saw that if we are having a differential equation and it's kind of an unusual differential equation, I mean, I don't think in the FEQ, maybe they do, at least when I was an undergrad, we didn't learn these, that if your excitement function in your differential equation is like the absolute value of a sine, how you can find the solution for the current. So this is how we did that. We broke down this into each harmonics, solved the differential equation one by one, then added up all of the currents with each other. All right. Questions? All right. So let's talk about the other way of improving the DC component in our output voltage. Remember, we just talked about, earlier in this class, we talked about, okay, if I want to get a better output current, or an output current which is closer to DC, I can put a resistor in series with the load. We just discussed that. We saw that. Now, you may argue that, well, another approach is to get a good output DC voltage, we can put a capacitor in parallel with the load. So that actually brings us to this other new topology that we are going to analyze. So we are looking at a full wave rectifier with an RC load. Okay? So now we are focusing here. All right. We have already analyzed a half wave rectifier with an RC load. This is kind of similar to that. It's just a matter of it's rectifying in full wave. As it turns out, let me see if I have a clear schematic. I thought I had it somewhere. Oh, here it is. Let me just put it down here. All right, so this is our schematic. Okay, so we have a full bridge of diodes, an H bridge of diodes, and then a capacitor placed in parallel with our load. Okay, so as it turns out, if I want to label these diodes to be D1, and D2, and then D3 and D4. Okay. when the input voltage is positive, so let me plot the input voltage waveform as well. I probably have it somewhere here. Okay, let me just use this one. Okay. And let's say this is our input voltage. Again, we have 4 diodes, 16 possibilities. We are not going to go through them. But as it turns out, if the input voltage is positive and basically it is trying to get larger than V out, then D1 and D2 conduct. So, okay, let me write this in blue because I'm going to use another color as well. So let's say this is our input voltage, okay? So as it turns out, I'm just trying to plot the output voltage, then we can further discuss it. But there are times that the input voltage is trying to get larger than the output voltage, and D1 and D2 do not allow that. So basically, they kind of clamp the input and output voltages with each other. So I'm trying to plot basically V out. All right? Then after that, the current of these 2 diodes, D1 and D2, the current tends to get negative. The diode cannot support that, so the diodes turn off. So here we have D1 and D2 on. Okay? Then when they turn off, let me erase this, write it in blue again. This is just my input voltage reversed. When the diodes turn off, basically I have an RC circuit going on over here, so it kind of gets discharged. So here all diodes are off. Until the negative value of the input voltage tends to get larger than the output voltage. In that case, D4 and D3 are going to turn on. Okay? So this is when D3 and D4 are on. And this lasts as long as these currents are, if you write the equation of the current of these diodes are, the currents are positive, this is going to last that much. And then beyond that, they're going to turn off. All right. So similar to what we saw before, there is a case that some diodes are on, then the current tends to get negative, the current of the diode, so they turn off. And then we have like an RC action going on until the next cycle or half of the cycle arrives. So if you want to plot the output voltage, it's going to look like, okay, let me continue this plotting. Something like this, all right? So this is going to be the waveform for the output voltage. All right, so we kind of can identify 3 modes. I would label this to be mode 1. In mode 1, D1 and D2 are the ones that are conducting. And I will identify this to be mode 2. In this mode, D3 and D4 are conducting and clamping the output voltage to the input voltage. And otherwise, we are in mode 3. That means all of the diodes are off. So this is mode 3, and this is also mode 3. So these are the 3 modes that you can identify. Okay, I'm going to stop here. If you have time, go through these notes. Very similar to the half-wave one that we did. Most of the equations are the same. There's a factor of 2 is added some places or reduced. So I'll see you guys next week on Tuesday. And please let me know if you are not able to download that Mathcad file from Blackboard.